Hello everyone, I am Dr. Shumayela Hasan from the Department of Economics, the BHOPAL School of Social Sciences. And here we are yet again in one more video that would explain you the second part of the chi-square test, that is the chi-square test of independence. As we know that chi-square test is a non-parametric test which is used on categorical data. So basically it is defined as a statistical method which is used to determine the association between two categorical variables. In our previous video also, we have had an elaborate discussion on what categorical variables and categorical data are. So therefore, please remember whenever you are using a chi-square test, whether it is goodness of fit test or it is the test of independence, it has to be used on category. If your data is in numerics, then the first step which you have to do is you have to convert the data into categorical data. Chi-square test is a test which is used to test the hypothesis, that is, whether there is no significant difference between the observed and the expected values, or there exists a difference between the observed and the expected values. It is one of the most important non-parametric tests of statistical analysis. As we had discussed in the previous module, there are two types of chi-square test. One is the chi-square test for goodness of fit, and the second one is chi-square test for independence. In the previous module, we will provide you the link for the previous module in the description box, so you can visit our previous module with the help of the link provided. We had discussed the goodness of fit test in detail. The basic difference between the goodness of fit test and the test for independence is that the goodness of fit test tests whether the expected values, that means that what you are expecting out of the data, you have certain expectations that how the data is going to behave, that is your expected value, and what you actually observe about the data, that will be your observed values. So whether there is a significant, that means statistically significant difference between the two or not. So in that case, you are going to use the goodness of fit test. But when it comes to the test for independence, the test for independence, that is the chi-square test for independence, is used when you have to test two variables for their association. That means if there are two variables, variable 1, whether it is connected or whether it is related, it has certain relation with variable 2 or not. So first and foremost, let's have a look at how to basically calculate the chi-square statistic. To calculate the chi-square statistic, that is the chi-square test, we need to calculate first the expected frequencies for each category and then compare it with the observed frequency. As I already mentioned, expected frequency is how you expect the data to behave, and observed frequency is how has the data behaved in reality. So let's first have a look at the formula for calculation of chi-square. Chi-square is equal to summation of observed minus expected frequency whole square divided by E, where O is the observed frequency and E is the expected frequency. So let us now discuss the chi-square test of independence in detail. A chi-square test of independence is a non-parametric hypothesis test. Now the meaning of non-parametric hypothesis test is it can also be applied to the data which do not follow the assumptions, basically the assumption of normality. Whenever the data is normal, most of the normal distributions are tested with the help of the parametric test, but when the data is not behaving normal, that means the test of normality, the distribution does not follow this normal curve. In this particular situation, it is always advisable to use the non-parametric hypothesis test. And one of the most famous and the most popularly and widely used non-parametric test is chi-square test. Okay. And as we have already mentioned, it is used on categorical variables. Now this was given by Pearson, so in most of the cases you may find people calling it as the Pearson's chi-square test also. Now Pearson's chi-square tests are non-parametric tests as it is already mentioned, and they are done on the categorical variables. Now they are used to determine whether your data is significantly different from what you were expecting it to be. You can use a chi-square test of independence, also known as the chi-square test of association. Why association? Because it is testing the association between two variables under study to determine whether the two categorical variables are related to each other or not. If two variables are related, the probability of one variable having a certain value is always dependent on the value of the other variable. Now, before I go on to do a numerical example with you, let us first understand one very important term related to the chi-square test of independence. That means, how do you organize the data into contingency tables? Now, what basically is a contingency table? When you want to perform a chi-square test of independence, the best way to organize your data is into a type of a frequency distribution, which is called as a contingency table. A contingency table, also known as a crosstab or cross-tabulation, it shows the number of observations in the combination of each groups. Okay, it is also usually inclusive of the rows and the columns. So, this is how a contingency table would look like. The data is organized in the form of or in the combination of rows and columns. So, these are the columns and these are the rows, row 1 and 2. So, this is cross tabulation of the rows and columns. This is how a contingency table looks like. So, there are 2 rows and 2 columns, so I can call it as a 2 by 2 contingency table. So, let us take a numerical example and see how the chi-square statistic for the test of independence is calculated. Imagine a city wants to encourage more of its residents to recycle the household waste. Now, the city decides to test 2 interventions, an educational flyer, that is a pamphlet, or a phone call. Now, there are the respondents, that means they randomly select 300 households. So, here your n is equal to 300 and randomly assign them to the flyer, phone call or the control group. So, here we have the third category, which is the control group. That means we are not intervening in their habit. There is no intervention at all. So, 2 types of interventions are being tested here. One is through a flyer or second is through a phone call. Now, they will use the results of their experiment to decide which intervention to use for the whole city. The city plans to use a chi-square test of independence to test whether the proportion of households who recycle differs between the types of interventions being used. Now, let us see the example further. Here are only 4 households mentioned. That means only the 4 addresses, although we have a list of 300. So, just for the example, we have mentioned 4 households. The intervention type is mentioned here and the outcome is mentioned here. So, with the help of the intervention of flyer, they are recycling, control group, that means no intervention, then again recycle, again control group does not recycle, phone call and they also recycle. So, the first thing what we have to do is we have to take the numbers pertaining to all these, that means flyers and how many of them recycle after being intervened by the flyers. Okay. Then we have to take the numbers, that means control group, not being controlled at all, and then how many of them without any intervention also are recycling and not recycling. So, with the help of the next slide, I think it will be more easier for you to see what the steps for conducting this particular test are. First and foremost, you have to define the null and the alternative hypothesis. Then you have to state alpha, then calculate the degrees of freedom. After that, you have to state the decision rule, calculate the test statistic, state the results and after that state the conclusions. Now, let us see how are we going to do this. So, this is the contingency table for the example at hand here. So, this is what has been given to us: flyer, phone calls and control groups. That means these are the 3 types of intervention. And after this intervention, if you can see here, 89 people are recycling and does not recycle is 9. Phone call, 84 people are recycling after the phone calls and 8 are not. Then without any intervention, the category has 86 people recycling and 24 not recycling. So, the first step is over, that is organizing the data into the contingency table. Here we have the data in the contingency table. Now, what you have to do with the contingency table is you have to find out the row totals and the column totals. So, how do we find out the row total? We will add these 2 categories and find out the row total. Again, add this and find out the row total, right. So, this is the row total, and here column total, how do you find out? Add all this and you will get the column totals here. So, finally, the check, this n should come out to be equal. That means, if you add these three categories, you should get n equal to 300, and when you add these, then you should get n is equal to 300. So, this is the first organization of your data into a contingency table when you have to proceed with the test of independence. This is the graphical representation of the data that we have collected here. Let us state the null hypothesis and the alternative hypothesis. Now, these two statements, if I may put it so, these two statements can act as a template for you in order to state your null hypothesis and the alternative hypothesis for the chi-square test of independence. You just have to replace the variables. So, if I may read this, variable 1 and 2 are not related in the population. The proportion of variable 1 and are the same for the different values of the variable 2. So, that means here whatever variables are under test, you can just replace these two variables and formulate your null hypothesis. Let us have a look at the alternative hypothesis HA. Variable 1 and 2 are related in the population. The proportions of the variable 1 are not the same for different values of variable 2. So, this can act as a template for you to frame your null hypothesis and the alternative hypothesis for the test of independence. You just have to replace the names of the variable 1 and the variable 2. Now, with respect to our example, what should be the null hypothesis and alternative hypothesis? So, whether a household recycles and the type of intervention they receive are not related in the population, this is stated as the proportion of households that recycle is the same for all interventions. So, this is the null, and the alternative hypothesis would be whether a household recycles and the type of intervention they receive are related in the population. So, we state it as the proportion of households that recycle is not the same for all the types of intervention. So, now let us test whether we are in a position to reject the null hypothesis or not. Now, the formula had two things which we had discussed previously: observed frequencies and the expected frequencies. The observed frequencies are already given to you in the numerical example. Now, the task in front of us is to calculate the expected frequencies. Now, how do we do it? For the expected frequencies, you have to multiply the row total and the column total and then divide it by n. So, with the help of the formula to calculate the expected frequencies, this is how your contingency table would look like. With the help of the interventions, that is the flyer, phone call and the control groups are no intervention basically. 89 was your observed frequency, and the formula to calculate the expected frequency is the row total into column total divided by the total number of observations. So, here we get the answer as 84.61. So, this becomes your observed and this is your expected. Similarly, you will calculate all the expected frequencies for all the other categories given. So, this is observed and this becomes your expected in the similar manner. Right. Let us proceed further. So, this is the formula that we have already discussed for the calculation of the chi-square test statistic. So, Pearson chi-square statistic test statistic is equal to chi-square is equal to summation of O minus E whole square divided by E. This is the symbol for chi-square, this is summation, O is the observed frequency and E is the expected frequency. So, here we again reorganize our data with respect to the observed and the expected frequencies that we have calculated. So, for all the types of interventions or the categories, we have the subcategories of recycle and does not recycle, and here we have written the observed and the expected frequencies. So, the further calculations will be done in this same table. So, the first step is to calculate the column O minus E. This is O and E. We just have to subtract the value of the expected frequencies from the observed frequencies, and here we retain the sign. Please see, this is minus, so we have kept it in minus. So, we do not have to take the absolute values, it is the actual values that we take. Next is we have to square this column O minus E whole square. So, you have to square this column raised to the power 2. and get your answers. Next is divide the entire column by E, that is the expected frequency. So, this is the expected frequency. So, basically this column gets divided by the expected frequency column and then we get the totals. So, here because we have the summation in the formula, so finally we add up the values that we have got in the last column and get the value of the chi-square statistic. So, this is the chi-square statistic that will be used to test against the p-value or the table value that we say in order to find out whether we are in a position to reject the null hypothesis or not. Right. So, the first step is contingency table, next is to calculate the chi-square statistic, and now we come to two more crucial things that we require for chi-square distribution test. Is first and foremost we have to look for the chi-square critical value in the table. So, with the help of two things we will be able to look for this critical value that will be compared against our chi-square test statistic. First thing is the degree of freedom and the next one is the significance level. So, how do we calculate the degree of freedom in this particular context? Number of variable 1 groups minus 1 multiplied by number of variable 2 groups minus 1. And the significance level, that means how much I am not confident that my answer would be correct, is 5% significance level that we have taken, like we take it for all the social science researchers in most of the cases. So, in our cases for the variable 1 group we have how many categories? 3 minus 1, that is 2, right, and for variable 2 group we have 2 minus 1. So, that means our degree of freedom would be 2 into 1, that is 2. We have to look up the chi-square table for 2 degrees of freedom and significance level of 0.05. So, here is the degrees of freedom is here and this is 0.05 is the significance level. So, the table value comes out to be 5.99147. So, the chi-square value that we had calculated is 9.79 and the critical value that we got from the chi-square table is the 5.99. So, now is the time to state the decision rule. If the value of the chi-square is greater than the table value, then we are in a position to reject the null hypothesis. In this case, the table value is 5.99. So, therefore, we can certainly say that we are in a position to reject the null hypothesis and accept the alternative hypothesis. Right. So, the chi-square value greater than the critical value. Therefore, the city rejects the null hypothesis that whether a household recycles and the type of intervention they receive are unrelated. There is a significant difference between the observed frequencies and the frequencies expected if the two variables were unrelated. This suggests that the proportion of households that recycles is not the same for all the interventions. Therefore, we are rejecting the null hypothesis. Thus, the city concludes that their interventions have an effect on whether the households choose to recycle or not. Thank you for watching. Stay tuned for more.